All right. We're going to, this isn't going to be quite as long as the previous one, but we're going to be looking at cylindrical coordinate system. In particular, evaluating triple integrals in cylindrical coordinates. So this is going to be useful when two of the variables may be better expressed in polar coordinates, but the third one in rectangular coordinates is fine. So generally, we're going to actually have the z variable be in rectangular coordinates and the x and the y in the polar coordinate sort of mode. So if you have some point, so the projection of some point that's given by a radius, so this is the picture that you want to have in mind in 3D space now. Some point here, the radius is going to go out to the, if we kind of look at that, the projection of this point down here on the xy plane, this is the length, this is the radius, and the angle here is theta, and then this length here is the length z. So we go out r units in the radius, theta radians away from the x-axis toward the y-axis, and then you go up or down in the z direction. So convert from r theta z, well, the z stays z, so that's really nothing interesting there. But the conversions are what we've seen before. To convert from r and theta back to x and y, x is r cos theta and y is r sine theta. And then the radius squared, r squared, is x squared plus y squared. And this might be handy once in a while. The tangent of theta would be y over x if you wanted to convert from y and x, and to get the theta, you can get it that way. So give an example of what something might look like in polar coordinates. Let's kind of sketch this thing out. So if r is equal to z, remember r squared is equal to x squared plus y squared. So that means r squared is equal to z squared is equal to x squared plus y squared. So the x squared plus y squared equals z squared for whatever z. The radius, the distance away from the axis is going to be equal to z. What we're going to find then is, let's say, like, let's take points where x equals 0, right? If x equals 0, we're going to have z squared equal to y squared. In other words, it's going to look like this. This is on the y z plane, and if y is equal to 0, you're going to get z squared equals x squared. That is to say, you're going to have the z value. See, it's a little hard to draw this to the perspective. I think what you're going to get is this these conical. Right, it's a conical. In fact, r equals z, the radius. The radius can never be negative, so this is as far as it'll. In fact, actually, if z is negative, having a negative radius is just going to mean it's going to be going on the other side of the circle. So actually, what you're going to have is really this on both sides of the x both sides of the xy plane. So the function, the equation r equals z describes this double-sided cone in 3D space. So when you're evaluating an integral in cylindrical coordinates, it's really the thing is your z is still going to be bounded, whereas before we would say z is bounded between u2 of x, y and u1 of x, y. We're instead going to write it as u2 of r cos theta and r sine theta, and u1 of r cos theta r sine theta. That's the conversion. And as before, when we converted to polar coordinates for integrals, you get an r with your dr d theta. They come as a package. You can't not have that r. So we replace f of x, y, and z with f of r cos theta, r sine theta, and z. So it's pretty straightforward, in fact, but it's just a matter of figuring out what the region of integration is. Here's an example. Let's figure this one out. We have a solid that lies within a cylinder x squared plus y squared equals 1, below the plane z equals 4, and above the paraboloid z equals 1 minus x squared minus y squared. So it's above this paraboloid. This is a paraboloid that's opening downward. So let's get a little sketch of this thing. It'll be helpful to have this in mind while we're doing this. So as you know, the cylinder that we're talking about is a cylinder that is a radius of 1 on the xy plane, right? It's below the plane z equals 4. 1, 2, 3, 4. And so like the top of this thing is going to be like a disk. And the paraboloid z equals 1 minus x squared minus y squared is going to be, it's going to be a downward opening paraboloid, but it's going to be looking like that. So what we have then is, it's like a can cylinder with a hollowed out bottom. Okay. So what we're going to set this up, we can have, since this is over a disk, we're going to go from 0 to 2 pi, and the radius is going to go from 0 to 1 because it's a disk of radius 1. Z is going to be the lower bound when we have z equals 1 minus x squared minus y squared. This is converted to 1 minus r squared using the conversion to from rectangular to polar coordinates. So that's the lower bound in the z direction. The upper bound is 4. So 1 minus r squared. Now the function, it says the density at any point is proportional to the distance from the axis of the cylinder. And so the density is given like this. So the density, the density function can be written actually as k times r. Okay, so k is some constant. So I'm integrating the function kr, and then I'm going to have r dz dr d theta. Now I'm going to integrate with respect to z first. Since there's no z's, what we're going to just get, and actually there's no thetas anywhere either. Might as well just evaluate the 2 pi, and then go from 0 to 1. What we're going to have is kr times 4 minus 1 plus r squared. Actually it's kr squared. And all that we have left is the dr to deal with. So 2k pi integral from 0 to 1, and this is just, we have 3 r squared plus r to the 4th dr. This integrates nicely, so 2k pi times r to the 3rd plus 1/5 r to the 5th from 0 to 1. When you evaluate this at 1, we're going to get 2k pi times 1 plus 1/5. That's, yep, it's 6/5. So that's going to be 6 times 2 is 12k pi over 5. That's going to be the mass. The mass of this thing that we've created. Here's another example. Now this is given in rectangular coordinates, but we want to use cylindrical coordinates. So z is bounded, so remember the conversion, that r is, or r squared is x squared plus y squared. And we can, let's see, we can, so if we want to convert parts of this. So first off, for the z, we are going to go between r and 2. And the function we're integrating is just the function r squared. And we do have to have an r and the dz, dr, d theta. But as far as the other bound, we need to figure out what that's going to look like. X goes from -2 up to 2. So what I'm doing is I'm graphing out in the xy plane, what is the region D, the shadow, look like? Now the function y equals plus, like when we're plus or minus the square root of 4 minus x squared, this is actually just y squared equals 4 minus x squared, otherwise known as x squared plus y squared equals 4. This is a circle of radius 2. So, okay, so that's, and so it's no wonder that this thing is going to be better put into cylindrical coordinates, right? In terms of cylindrical coordinates, my angle just goes from 0 to 2 pi, and my radius is just going to go from 0 to 2. And so this is not too hard to evaluate now. Now there's no z, so actually, and there's no theta, so I'm going to have a 2 pi times the integral from 0 to 2 of r to the third times 2 minus r. And then we have the dr. Right, the r to the third was just this. And then the integral is the 2 minus r. That's 2 pi 0 to 2, that's 2r cubed minus r to the fourth dr. Let's do the integral now. We have 2 pi times, that's going to be 2/4 r to the fourth minus 1/5 r to the fifth from 0 to 2. This is 2 pi times, what is it? It's going to be 2/4 times 2 to the fourth, that's going to be a 16, and minus 1/5 times a 32. 16 pi over 5. Okay, so I told you this was going to be a quick one, relatively short, and we'll just do more practice in class, and you'll see that that it's the tricky part is perhaps converting from the rectangular to the polar coordinates, but and remembering, don't ever forget that you have r with that comes with the dr d theta. Like they come together always when you convert to polar coordinates or cylindrical coordinates. Well, the reason is because the x and the y are being converted to polar coordinates, right? And if you don't remember why, it's because little tiny rectangles in polar coordinates, the size of them is proportional to the radius, how far away it is from the origin. So go and watch that previous lesson if you're not sure what I'm talking about. Okay, all right, bye.